In this video, I'm going to work through two examples of solving complex circuits. When we solve a complex circuit, we're basically doing the same thing we did with our other circuits. We're trying to find the voltage, the current, and the power of each resistor. A complex circuit is one in which we have multiple batteries providing multiple pathways for the current to flow. We don't approach these circuits the same way we did the others. In these circuits, we have to use Kirchhoff's laws to write equations in order to solve for the missing currents through our circuit, and that will allow us to get the current, voltage, and power of each resistor. In this first circuit, I see two batteries, 24 volts, 12 and 20 volts, and three resistors, 10 ohms, 14 ohms, and 6 ohms. We solve this by looking at the sections of the graph or the sections of the circuit in which current flowed. So we're going to have current flowing through this part. We'll call that A. We'll have current flowing through this part. We'll call that B. And we'll have current flowing through this part. We call that C. Now, we actually don't know which direction the current's flowing in each of those sections, but we have to pick a direction or assign a direction. Now, this doesn't have to be random, where we just flip a coin and say, well, is circuit A, in the current in A, is that going to the right or to the left? We can look at our battery. Now, the positive is the longer end of the battery, which pushes conventional current away from the positive. So in this part, since the battery is pushing current to our left, or counterclockwise, we'll assume that current is flowing in that direction. Through the bottom, we have our positive of our battery on the left side again, and so it's going to be pushing current to the left. Now, if we assume the current goes this way, we might be correct, but we might not be correct. If we end up guessing the wrong direction, it'll show up in our answer, and we'll recognize that and be able to interpret it. Now, in section C here, we can assume, since current is flowing in to this junction from the top and the bottom, that it would flow to our right. So those are our assumed current directions in each of the sections. Now, I'm going to write Kirchhoff's loop equations for two different loops here. So I've got a loop at this part where, if we remember, the voltage of every resistor we pass through will add up to equal the voltage of the battery. As long as we're going with the current, with our assumed current direction, we'll write our equations with the same positive or negative signs that we normally would assume. So if we start out at our battery, we're going to have our 24 volts will equal the voltage across resistor 2, which is current through resistor 2 times R2. So that's I2 R2 plus, we'll go through resistor 3, and that's I3 R3. But resistor 2 is 14 ohms, resistor 3 is 6 ohms, and our current number 2, that's C, and our current 3, that's A. So I can rewrite this as 6 current A plus 14 current C equals 24. So that's my first loop equation. If I write a loop equation for this bottom loop, we'll have our 20-volt battery, and that will equal the current through resistor 1 times R1, I1, R1, plus I2, R2. So that complete loop, voltage plus voltage equals battery voltage. So I can rewrite this equation again, because since R1 is 10 and R2 is 14, then I have I1, current through resistor 1, that's my B, and the current through 2, that's our C. So I'm going to have 14 IC plus 10 IB equals 20. That's our second equation. Now the third equation we're going to write uses a junction. So the two junctions that are relevant here are to the far left and to the far right. Remember, Kirchhoff's junction rule says the current going into the junction equals the current coming out of a junction. So going into this junction is current A and current B. So they're going to add together to equal the current coming out, which is current C. Those are our three equations. We need as many equations as we have unknowns. And we have three unknown currents, A, B, and C, and now we have three equations. So the rest of this is pure algebra. If IC is IA plus IB, we can substitute into these two equations. So we can get, if we rewrite this equation, we get 6 times the current A plus 14 times the current C, which is IA plus IB. That's going to equal 24. And then we substitute it into the second equation. We're going to have 14 times IC, which is IA plus IB, plus 10 IB equals 20. Now if we reduce and combine like terms, we're going to get 6 IA plus 14 IA, that's 20 IA plus 14 IB equals 24. And we're going to have 14 IA plus 14 IB plus 10 IB, that's 24 IB equals 20. Now we have two equations and two unknowns. These can be solved by substitution or linear combination. So we can reduce them. We can divide everything by 2 in this case and get 10 IA plus 7 IB equals 12. And we can get 7 IA plus 12 IB equals 10. So how you go about solving this is a matter of choice. I like to do linear combination. So if I multiply this top equation times 7 and this bottom equation times 10, I'll end up with 70 IA and 70 IA, which will cancel out. So I'm going to have 70 IA plus 49 IB equals 12 times 7, which is 84. And I'm going to have 70 IA plus 120 IB equals 100. Multiplying the bottom equation by 10. So now I can subtract one equation from the other. So 70 minus 70 is 0. 49 minus 120 is negative 71. IB equals 84 minus 100, which is negative 16. So that's going to tell me that the current in section B is negative 16 divided by negative 71, which is 0.225, and that would be amps. So that's the current in section B. Now to find the current in section A, I can substitute that value into one of my other equations. So I can go 10 IA plus 7 times 0.225 equals 12. So that means that 10 IA plus 7 times 0.225, that's 1.575, equals 12. So 10IA is 12 minus 1.575. That gives me 10.45. So now we divide by 10, which I really don't need a calculator, but I get a 1.04. And if I round off, it doesn't look right, does it? 12 minus 1.575 is 1.425. Forgot that. So that's 10.425, round off to 1.03. So that's the current in A. The current in section C is IA plus IB. So the current in section C will be 1.043 plus 0.225. That's 1.268. So there are my 3 currents in each section. So now we go up to our chart. The current through resistor 3 was current A. So that's 1.043. The current through resistor 2 was C, 1.268. And the current through resistor 1 was B, 0.225. To get the voltage, I multiply current times resistance. So 0.225 times 10 will be 2.25. 14 times 1.268 is 17.75, and 6 times 1.043 is 6.26. Power, volts times amps, so 2.25 times 0.225, I get 0.506. Then I take 17.75 times 1.268, and I get 22.51. And then 6.26 times 1.043, I get 6.53. So there's my answers. Now, are they correct? Well, will voltage 2 plus voltage 3 add up to equal 24? Well, that's 23.101, so 24.01. So that works out. Will voltage 1 plus voltage 2 add up to equal 20? Yes, they do. So if all of that works out, we can assume we got the answer correct. So this is one in which it was fairly obvious which way the current would be flowing in each section because of the way our batteries are arranged. But in this next example, I'm going to do one where one of the batteries is turned the opposite direction. So now we see a circuit in which one battery faces to the right, the other faces to the left. We start out the same way. We've got 3 sections. There's one, here's one, and here's the other. And we can call these A, B, and C, just like we did before. Now we have to try to come up with a good estimate of which way the current will be flowing. Because the battery, the 24-volt battery, positive pushes to the left, I'm going to go ahead and assume it's that direction. This one pushes to the right, which is that direction. But in the middle, do we think that this voltage and current pushing this way will dominate the current coming from this one that would go this way? Which one of those do we think is bigger? You say, well, this one's got a 24 volts, so it's more powerful, so it would push harder than the 22 volt, but the 22 volt has a bigger resistance, so that'll mean it has less current. R3 is a little less, so I'm going to assume it again is this way. Now, if we make the wrong assumption when we're solving for our currents, we'll end up with a negative value. If you end up with a negative value for your current, all that means is that the current was actually going the other direction, that you assumed the wrong direction. But we're going to do this the same way. We're going to write our loop equations. So the first one I'm going to write is my 24 volts will equal I3R3 plus I1R1. Now if I go ahead and substitute in, R3 is 6 and I3 is current A, so I'm going to call that 6IA plus I1 is IC and R1 is 12, so that's 12IC, and that's going to equal 24. Now I can divide all of that by 6 and get IA plus 2IC equals 4. So there's one equation. For the next loop, my 22 volts equals, this will be I2R2, and then the next one is I1R1, but here's where it's different. Because we are moving in the opposite direction of our assumed current, we now make this a minus. That's important. So whenever we're following this loop, as long as we go with the flow, the voltages of the resistors will add up to equal the battery voltage. But if we go against the flow like we are through resistor 1 in path C here, we subtract it. So when I substitute in, R2 is 8 and I2 is current B, so I have 8IB minus resistor 1 is 12 and that's IC. That's going to equal 22 volts. This one I can divide everything by 2 and get 4IB minus 6IC equals 11. So there's my second equation. Third equation will be a junction. Now in this junction, only current A goes in, current B comes out of it, and current C comes out of it. So IA equals IB plus IC. That's my third equation. So I have three equations with three unknowns, A, B, and C. So we go about solving this the same way we did the other. IA is IB plus IC, so I can substitute IB plus IC plus 2IC equals 4. So that gives me IB plus 3IC equals 4. When I substitute in this second equation, or actually I don't have to substitute because I have IB and IC, so I can take these two equations and solve for IC. So I'm going to do the linear combination again. I'm going to take this equation, 4IB minus 6IC equal 11, and I'm going to multiply this bottom equation by 4. That'll be 4IB plus 12IC equals 16. Then I'm going to subtract. So 4IB minus 4IB is 0. Negative 6 minus 12 is negative 18 IC. That equals 11 minus 16, which is negative 5. So that tells me that IC is 5 over 18, which is 0.278. That would be in amps. So that's current C. So I can substitute that value into this equation. So IB will equal 4 minus 3IC, which is 4 minus 3 times 0.278. So 3 times 0.278 is 0.834. So 4 minus 0.834 is 3.166, and that's current B. And now that I know C and B, current A is B plus C. So current A is 3.166 plus 0.278 is 3.444. Now I know all three currents. So I go back up to my chart. You say, okay, number 3, that was IA, so that's 3.444. Resistor 2, that was current B, 3.166. And resistor 1, that's current C, 0.278. So again, the volts is current times resistance, so 0.278 times 12 gives me 3.34. And then 8 times 3.166 gives me 25.33, and then 6 times 3.444 gives me 20.67. Then the power, 3.34 times 0.278 is 0.93. 25.33 times 3.166 is 80.19, and 20.67 times 3.444 is 71.19. So to check this, does voltage 3 plus voltage 1 equal 24? 20.67 plus 3.34 is 24.01. So that checks out. And then, for this one, does 22 volts equal voltage 2 minus voltage 1? 25.33 minus 3.34 equals 21.99, which is our 22. So this checks out. So the most challenging part of solving a complex circuit is making sure that you get a minus sign in a loop equation when it's needed. Now, if I had worked this out assuming that C went to the left instead of the right, when we solve for current C, I would have gotten a negative value. That would tell me that the current was actually going the opposite direction. But in our chart, we want all positive values. So you have several of these complex equations to work out on your own. The two examples I've just done are the same circuits you have to work out. I just changed the numbers slightly.